Okay, so we have looked at the Cauchy integral formula, this powerful result about analytic functions and how the value of an analytic function at a point can be written in terms of its values along the whole contour around it, right? So, and that contour can be quite far away from the point of interest, provided the entire region is a region of analyticity. So, in this lecture, we will see how we can go further. So in fact, the derivatives of an analytic function can also be written in terms of similar integrals. So that's what we will discuss in this lecture. Okay, so the Cauchy integral formula, as we have seen, is f of z. Well, we wrote it as f of z naught, right? But if you use the label z, so f of z, and then there's some dummy variable w, uh, you consider a contour C which encloses this point of interest, the point of interest being Z, and so we are given that this function f of z is analytic everywhere in the region enclosed by this contour, including the points on the contour. Then we have seen that this contour integral 1 over 2 pi I contour integral C f of w divided by w minus z dw is in fact the same as the value of the function f of z. Right? So now we see that f of z is a function of z, and on the right hand side we have this complex variable w, which it gets integrated out. So in some sense it's a dummy variable, right? So we would like to take the derivative of this function f of z with respect to z, right? So we know that it's an analytic function, so we are guaranteed that the derivative exists. It has there is a meaningful limit at that point, and so we are guaranteed that this derivative exists. So we can actually go ahead and take this derivative like we typically would for this function 1 over w minus z, right? So the procedure is the so-called taking of the derivative under the integral sign, right? So we are probably familiar with this technique when we are working with functions of a real variable. So f prime of z is equal to 1 over 2 pi I. So we have f of w will remain as it is. The only dependence on z within the integrand comes from this 1 over w minus c. So you get minus 1 over w minus z the whole square times minus 1. So it's just f of w divided by w minus z the whole square. So in fact, this is like a Cauchy integral formula for the first derivative of this function f of z. Right? So technically speaking, this is the validity of this operation would require some more justification, but we will accept this. So this is indeed correct, and it can be argued for from first principles, but we will take this as a reasonable argument, and indeed it is true. F prime of z is given by this form. Cauchy integral like form. It's another integral, and so what we observe is f prime of z is also an analytic function. So let's write this down formally first of all. So if you're given a function f of z, f of z is analytic, and so when you take the first derivative, f prime of z is also analytic. And in fact, you can go ahead and take a derivative again. And so if you do this same procedure repeatedly n times, you can do it. And so in general, so the result is that if a function f of z is analytic everywhere inside and on a simple closed contour C taken in the positive sense, and z naught is your point of interest, which is interior in the interior of C, then we can find out the nth derivative of this function, and the value of this at the point z naught is simply given by n factorial divided by 2 pi I, right? So this factorial will come in because when you take a derivative once, it's just w minus z squared, but if you take a derivative again, then you'll get 2 divided by w minus z the whole cube, then you'll get a 2 times 3. So in general, if you take the derivative, at the nth derivative, you're going to get an n factorial divided by 2 pi I as it is. Then the contour integral is now f of z divided by z minus z naught to the whole power n plus 1. So I have again gone back to older notation. So I'm looking at this point z naught, and then n can be 0, 1, or 2, and so on. So n of n equal to 0, of course, refers to not taking any derivative. That's the the standard Cauchy integral formula, right? So what this tells us is that if a function is analytic in some region, then the value of not only the function f of z is determined by the values that this function takes, along some contour, right, which encloses this and which encloses an entire region of analyticity, but in fact all the derivatives of this function at that point are given by the values of this function on such a contour, right? So in fact a consequence is of course that if a function is analytic, then it's every derivative, higher order derivative must exist, right? So this is quite different from how the scenario in functions of a single variable, right? So you may have a very nice looking function, but and who has a well-defined derivative, but the second derivative may not exist, or a third derivative may not exist. But such a situation is impossible for an analytic function. If its first derivative exists, then second derivative exists, third derivative exists, and in fact all derivatives to all order are automatically present, right? So this is the extra power that analyticity gives you. So let's look at a few examples of how one can exploit this formula. So suppose you have this unit circle mod z equal to 1 oriented in the anti-clockwise sense, and suppose you consider the function e to the z, right? F of z is analytic on and within C. So considering the point z naught equal to 0 and applying the Cauchy integral formula, it's just a direct application of this result. If you take e to the z and divide by z to the power 4, and you have dz, so z naught is taken to be 0 here, right? So and therefore according to this formula we must get 2 pi I divided by 3 factorial, and the value of the third derivative of this function evaluated at 0. But the third derivative of this function is the same as the first derivative and is the same as the function itself, because we're looking at e to the z. So if you take the derivative of e to the z, you can get e to the z again, and then repeated differentiation also leaves the function unchanged, right? So this is exactly like how the function behaves even with function of a real variable. So therefore you simply get 2 pi I divided by 3 factorial times e to the 0, which is 1. So it's 2 pi I by 6, which is just 1 by 3 pi I. So that's the answer. You can look at another example. So if z naught is some interior point, that is enclosed by this positively oriented simple closed contour C, and if you take the function itself to be just 1, right? So it's a constant and it is 1. So of course it's analytic. So if you do 1 over z minus z naught, right? So this contour can be any simple closed contour, right? So we are not defining this contour with any greater specificity. So but 1 over z minus z naught dz is just 2 pi I, 0 factorial f to the 0 of 0 is the same as saying you don't do anything, it's just this function as it is, which is 2 pi I, right? So this is the result which we have already seen. If you take 1 over z minus z naught dz, contour integral about this point which encloses z naught is going to be 2 pi I. But if you take any higher order derivative, right? So 1 over z minus z naught the whole power n plus 1, where n is greater than or equal to 1, right? So then you're going to get 2 pi I by n factorial f, the nth derivative of this function of 0. But even the first derivative of this function is just 0, and then of course all subsequent derivatives are all 0. So indeed this is equal to 0. So this is also a result which we saw, right? We saw that the contour integral of 1 over z dz alone is 2 pi I. If you have positive powers also, it gives us 0, z to the n dz, whether n is a positive integer or a negative integer, we saw that it's 0, unless except for this very special value 1 over z, where n is equal to minus 1, right? I mean, we basically are seeing the same result using this Cauchy integral theorem, and of course generalized to an arbitrary point z naught. It doesn't matter, there's nothing sacrosanct about this result about the origin. It can be about any point z naught, and that's what we have explicitly seen here. Okay, so there's a few consequences which immediately come from this Cauchy integral formula for the derivatives. So let's just collect them here. So if you have a function f of z which is analytic at a given point, then all its derivatives of all orders are also analytic, right? So this is something that I already mentioned, right? So this comes from the fact that you have well-defined derivatives, right? So the existence of a derivative for f of z, so if f prime of z is defined at a point, right, and we have seen that it's also the whole region around this point is also analytic, right? So therefore f prime of z by a similar Cauchy formula is going to be defined in this entire region around this point z. Therefore f prime of z is not only is f prime of z defined, but it's also analytic, right? Because f prime of z is defined in a whole neighborhood, and likewise every order thereafter is also going to be in an analytic function. So you can keep on differentiating as many times as you want if you're working with an analytic function. Now it's also true that if f of z is continuous on a domain, and if we can be sure that the contour integral, any closed contour integral of this function f of z is 0, then it's guaranteed to be analytic, right? So we have seen that this idea of continuity on a domain coupled with this need for every closed contour integral of this function being 0 is equivalent to the existence of an antiderivative, right? And if the antiderivative exists, and so we can argue that it's basically analytic in this region, right? So these are immediate consequences of the existence, the generalization of this Cauchy integral formula. So for our purposes, we want to look at analyticity, and all its properties without necessarily going into any rigorous proofs as such. But for the integral formula, we did give a fairly convincing argument for how that comes about. But in general, so the point is that if you have a function f of z which is analytic, it's going to be analytic in a region, and derivatives to all orders are immediately available, and all these derivatives are also analytic. And so the statement that a function is analytic in some region is equivalent basically to the statement that all these closed contour integrals of this function are also going to be 0, right? So which is also related to the fact that at every point f z you can associate an antiderivative to this function, so it doesn't matter which path you take. So this is also very closely related to the path independence of contour integrals, which does not involve closed paths. So you can always think of if you're going from a point z1 to z2 along one direction, but then you should come back along a different direction. Then if you're guaranteed that such a closed contour integral is 0, so basically what it means is going from z1 to z2 along one path must be equal to going from z1 to z2 along another path, because when the moment you have a closed contour integral, which means that the path independence is immediately a consequence of every closed contour being 0, right? So as you can immediately sort of intuitively see, right? So in this lecture we looked at how the Cauchy integral formula can be extended to higher order derivatives, and the fact that derivatives to all orders exist and are analytic for any analytic function. Thank you.